QFT, and after that we measured the probability for some y's that we call good, for some vectors that we call good. And here's this probability for any of these good values, good vectors. Now, why do we care about this? Let's recall our definition of goodness, and let's write it without this absolute value here. So, to be a r y modulo n divided by n is less or equal than pi and greater or equal than minus pi. And we are going to divide everything in this double inequality by this, by 2 pi a, and multiply by this, by n. And you remember that a divided by n is approximately 1 divided by r. So what we have here is minus r divided by 2 less or equal r y modulo n less or equal r divided by 2. And now we are going to get rid of this modulo n, so we can write r y is less or equal than nk plus r divided by 2 and greater or equal than nk minus r divided by 2. And what we can see here is that for any particular k, we can solve this double inequality and find particular value y. So when k equals to 0, we have y0, which itself equals to 0. For k equal to 1, we get some y1. K equals to 2, we get y2, etc. And when k equals to r, we have yr has to be equal to n, which is 0 modulo n. And we have to start over. So there are only r different good y's. And we have the probability of measuring each of them. So the probability of measuring any good y is this probability of measuring one of them multiplied by the number of good y's, which is 4 divided by pi squared, and it is almost 1/2. So we see that with reasonably good probability, after the QFT, we measure some y's that we call good. And now it's time to explain why we call them. So why we call them good, and why do we care about measuring these particular vectors? Okay, it's time to unveil the reason why we call these y's good. So this is one of the definitions of goodness, and we are going to divide it by n and by r. Okay, so this, if we divided by n and by r, we get y divided by n is less or equal. This would be k divided by r plus 1 by 2n. And here we will have 1 divided k divided by r minus 1 by 2n. And that means that in the very near this number, which we can compute because we have measured y and we have n, there is a number k divided by r, and the distance between them is less than this. So it's very short distance. So what? Okay, we have this this inequality saying that near this number we can measure there is this number, which is interesting to us because of this r. And if r is less than square root of n, then here in this distance from y divided by n can be only one number with this this quality. Why? Let's see why. If we have, for example, two denominators, r1 and r2, each such as r1 less than square root of n and r2 less than square root of n, and we have two fractions, a divided by r and b divided by r2, what can be the distance between these numbers? And we assume that these numbers are not equal. So we compute the distance, and equals to a r2 minus b r1 divided by r1 r2. And since these these fractions are not equal to each other and a and b are integers, it is greater or equal to 1 divided by r1 r2, and this is greater or equal than 1 divided by n, because we have this these inequalities for r1 and r2. So if we have two fractions with the denominators which are less than square root of n, then the distance between them must be greater than this. If r happens to be less than square root of n, which is likely because n is quite a big number, then this value, k divided by r, is the only value with this quality in this neighborhood of y divided by n. So we have y divided by n, we have this neighborhood of the size 1 divided by n, and we can search in this neighborhood for the fractions with the denominators less than the square root. And if we find one, and if y was good y, then we get this fraction k divided by r, and we either get r or one of its denominators. But how to search for this number, which is close enough to this measured number with this small denominator? By the continuous fraction method. Let's see an example of this.